Welcome to Cambridge IGCSE Physics, Lesson 46.1, Force on a Wire in Magnetic Field. Today we explore the motor effect, where current-carrying conductors experience forces in magnetic fields. This fundamental principle underlies electric motors and many modern technologies. We'll examine experimental demonstrations and understand how reversing current or field direction affects the force. This core content builds essential knowledge for your IGCSE physics examination and future studies. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, describe the experiment showing force on a current-carrying conductor. This means explaining the apparatus, method, and observations clearly. Second, show the effect of reversing current direction. You'll understand how changing current direction affects force direction. Third, show the effect of reversing magnetic field direction. This demonstrates how field orientation influences the force. These objectives align with Cambridge IGCSE assessment, focus on experimental skills and core understanding. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, motor effect, which means the force experienced by a current-carrying conductor when placed in a magnetic field. This is the fundamental principle behind electric motors. Second, current-carrying conductor, which means a wire or other material through which electric current flows. The moving charges create the interaction with the magnetic field. Third, magnetic field, which means the region around a magnet where magnetic forces can be detected. Understanding these terms precisely is crucial for exam success. Let's explore the motor effect, our first core concept. The fundamental principle states that a current-carrying conductor experiences a force when placed in a magnetic field. This means when electric current flows through any conductor, such as a wire, and that conductor is placed in a magnetic field, a force acts on the conductor. The definition is, the force acts perpendicular to both the current direction and the magnetic field direction. Key features include force direction depends on current direction, force direction depends on field direction, and force magnitude depends on current strength. The diagram illustrates a vertical wire carrying current upward placed in a horizontal magnetic field pointing right. The resulting force acts into the page shown by the cross symbol. Notice how all three quantities are perpendicular to each other. Now we examine the experimental method. This follows Cambridge IGCSE standards for demonstrating the motor effect. The apparatus needed includes a low-voltage power supply for safety, connecting wires to complete the circuit, a horseshoe magnet to provide the magnetic field, and a copper rod as the current-carrying conductor. The method consists of these steps. First, place the copper rod between the poles of the horseshoe magnet. Second, connect the rod to the power supply using the wires. Third, switch on the current and observe the rod's movement. The observation shows the rod moves perpendicular to both current and field directions. Safety is paramount. Use only low-voltage supplies to prevent electric shock and avoid short circuits which could damage equipment. The diagram shows the complete setup with the rod positioned between north and south poles, connected to the power supply, with the resulting upward force clearly indicated. Let's work through our first example. The problem states, a horizontal wire carries current of 2.0 amperes from left to right in uniform, magnetic field of 0.05 Tesla, pointing into the page. Describe the direction of force on the wire. We are given current I equals 2.0 amperes flowing from left to right, and magnetic field B equals 0.05 Tesla, pointing into the page. We need to find the direction of force on the wire. Step 1. Apply Fleming's left-hand rule for the motor effect. This rule helps determine force direction. Step 2. Point your first finger in the magnetic field direction, which is into the page. Step 3. Point your second finger in the current direction, which is from left to right. Step 4. Your thumb now points in the force direction. The result is, the force acts vertically upward on the wire. Example 2 demonstrates the effect of reversing current direction. The problem is, investigate how reversing current direction affects the force on a wire in a magnetic field. The setup shows a wire in a magnetic field with current initially flowing upward. Now we analyze systematically. First, In the original situation, current flows upward, magnetic field points right, and force acts into the page, shown by the cross symbol. Second, when we reverse the current now flows downward, but the magnetic field still points right. Third, applying Fleming's left-hand rule to the new situation, the force now acts out of the page, shown by the dot symbol. Fourth, we conclude, reversing the current direction reverses the force direction. The diagram shows both situations clearly, with the original force into the page and the reversed force out of the page. Mathematical skills are crucial for analyzing forces on wires. Let's examine 3 key skills. First, Fleming's left-hand rule provides a systematic method for determining force direction. Your first finger points in the magnetic field direction, from North Pole to South Pole. Your second finger points in the current direction, from positive terminal to negative terminal. Your thumb then points in the force direction, showing which way the conductor will move. Second, vector analysis helps understand the 3-dimensional nature of the problem. The force is always perpendicular to both current and magnetic field directions. Use a right-hand coordinate system to visualize 3-dimensional problems clearly. Third, experimental variables must be identified correctly. The independent variables are current direction and magnetic field direction, which we can control. The dependent variables are force direction and magnitude, which we observe and measure. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, a wire carries 3.0 amperes current northward in an eastward magnetic field. State the force direction. Use Fleming's left-hand rule to solve this systematically. Question 2 is intermediate level. It states, describe what happens when the magnetic field direction is reversed in question 1. This requires you to apply the concepts we've learned about reversing field direction. Question 3 is advanced level. The question is, explain why no force acts on a wire when it is parallel to magnetic field lines. This tests your understanding of the perpendicular relationship between force, current, and field. For all questions, remember to use Fleming's left-hand rule systematically, show your reasoning clearly, and explain your answers in terms of the motor effect principles. Physics principles power our modern world. Let's see how today's concepts apply in practice. In electric motors, the motor effect converts electrical energy into mechanical energy. Current-carrying coils in magnetic fields experience forces that create rotational motion, powering everything from household appliances to industrial machinery. In loudspeakers, a voice coil carrying audio current sits in a permanent magnetic field. The varying current creates varying forces that move the speaker cone, producing sound waves that match the electrical signal. In magnetic levitation trains, electromagnetic forces lift and propel the train without physical contact, reducing friction and enabling high speeds. These applications demonstrate why understanding the motor effect matters. Career-wise, this knowledge leads to electrical engineering, where you design motors and control systems, automotive engineering for electric vehicle development, and renewable energy systems for wind turbine generators and solar tracking mechanisms. Let's review the solutions. For question 1, using Fleming's left-hand rule, point your first finger eastward for the magnetic field direction. Point your second finger northward for the current direction, and your thumb points upward. Therefore, the force direction is upward. For question 2, when we reverse the magnetic field from eastward to westward, first finger points west, second finger still points north for the current, and now your thumb points downward. The force reverses to the downward direction. For question 3, when the wire is parallel to magnetic field lines, the current direction and field direction are parallel, not perpendicular. The motor effect requires a perpendicular arrangement between current and field, so no force acts on the wire. Exam success tips. First, use Fleming's left-hand rule systematically for all direction questions. Second, state clearly the field direction, current direction, then conclude with force direction. Third, remember that reversing either current or field direction reverses the force direction. Fourth, explain your reasoning using motor effect principles in longer examination answers. Let's summarize today's lesson. The key points to remember are, first, the motor effect occurs when a current-carrying conductor is placed in a magnetic field, resulting in a force perpendicular to both current and field directions. This fundamental principle underlies all electric motors and many electromagnetic devices. Second, direction rules require systematic application of Fleming's left-hand rule, where your first finger represents magnetic field direction, second finger represents current direction, and thumb shows force direction. Practice this rule until it becomes automatic. Third, reversibility means that reversing either the current direction or the magnetic field direction will reverse the force direction, while reversing both returns the original force direction. For further study, practice Fleming's left-hand rule with different three-dimensional orientations to build confidence. Review experimental procedures carefully as practical assessments often test this topic. The next lesson covers electromagnetic induction, which is the reverse process where motion in magnetic fields generates electrical effects.